Hello everybody. Let us look into degenerate eigenvalues in quantum mechanics. A Hermitian operator, which will be also called observable. Why? Because we are considering those operators which can be measured. So an operator which can be measured is termed as observable. So a Hermitian operator A can have eigenvalues with multiplicity greater than 1. That is, more than one linearly independent eigenvectors correspond to the same eigenvalue. Now, this is an important point in the quantum computing concepts, where when we perform the measurement of the quantum system, first of all, the observable has to be Hermitian, because the Hermitian operator will have real eigenvalues, and when we measure the quantum characteristic or the observable or the property of the quantum system, then the Hermitian, since the operator is Hermitian and it will have real eigenvalues, so therefore during measurement the measurement outcome will also be real. So that is the condition for the for an observable, so that we can perform so that we can do the measurement. A Hermitian operator A, so this operator, which is basically a matrix, will have eigenvalues. Now the eigenvalues can have multiplicity greater than 1. This is a case of degenerate eigenvalues. So what are degenerate eigenvalues? When any one eigenvalue, any one or more eigenvalues will have more than one eigenvectors associated with them. So if an eigenvalue has got more than one eigenvector associated with it, then it is a case of non-degenerate eigenvalues. If every eigenvalue has got distinct eigenvectors, then this is a case of non-degenerate eigenvalues. So if an eigenvalue has got more than one eigenvector associated with it, that will be termed as the multiplicity. So that is why I am saying the eigenvalues will have multiplicity greater than 1. That means more than one eigenvectors are associated with an eigenvalue. Therefore, let us consider you have an eigenvalue A and it has degeneracy D. That means D eigenvectors are associated with this single eigenvalue. We will say that this degeneracy of D, that means D eigenvectors will form an eigenspace associated with this eigenvalue A, and this eigenspace will have dimension D. Now what is this eigenspace? This eigenspace is basically related to the degeneracy of the eigenvalue. Degeneracy means this eigenvalue has got more than one eigenvector associated with it. If this eigenvalue has got an eigenspace of dimension D associated with it, that means D eigenvectors are associated with the same eigenvalue. So let us take an example here. An operator A has eigenvalue lambda equal to 3 with multiplicity 2. That means with this eigenvalue lambda equal to 3, two eigenvectors will be associated. So therefore we can write two eigenvalue equations. One is this, the other is this. Same eigenvalue but different eigenvectors. In this case, the eigenspace is two-dimensional, particularly related to the degeneracy. Now let us look into the projection operators for the degenerate subspace. For degenerate eigenvalues, the projection operator projects onto the entire eigenspace, not just a single vector. So what happens in the normal case, when there is no degenerate eigenvalues, the projection operator will project onto the eigenstate, onto that particular eigenstate. But in the case of degenerate eigenvalues, the projection operator will project onto the entire eigenspace. Now this eigenspace is not for all the eigenvalues. This eigenspace that I am talking here is for that eigenvalue for which we have more than one eigenvectors, and the number of eigenvectors will form an eigenspace for that eigenvalue. So therefore this is the degenerate eigenspace. In this case, the eigenvalue now will be updated. The final eigenvalue equation will be updated, and this is the updated equation. Here, if you do not, if you assume that I is not there, this is a normal eigenvalue equation, and n represents the number of eigenvalues. Now, since I superscript has come, this actually indicates the degeneracy dimensions, number of eigenvectors associated for that particular eigenvalue. This is how we will update the eigenvalue equation. That is, there are Gn eigenstates that share the same eigenvalue. So we can express the quantum state also as had there been no degeneracy, then there would have been only one sigma indexed as n. But since degeneracy is there, we have to take care of the degenerate eigenspace. So therefore the second sigma will come, for which I will vary from 1 to Gn, and I index is brought into the equation at the superscript level. And coefficients, as you know, are given by the projection of psi onto the eigenstate. Since this eigenstate has got an eigenspace because of the degeneracy, so that's how this I superscript I variable will come. I have just tried to explain the two sigmas also, where sigma n is over distinct eigenvalues and sigma I will take into account the degeneracies of the eigenvalue. Now let us look into the and I have already discussed about the probabilities also, that the probability equation will also change with probability of that particular eigenvalue, because in this case the probability will not be this means the probability of this eigenvalue is not related to one eigenstate. So there will be an eigenspace. So the magnitude squared terms will be a summation of all the eigenvectors for which this eigenvalue is there. Now projection operator will accordingly be modified. In this case, had there been no degeneracy, I would not have been there, and the projection equation should have been without sigma, and the projection equation should have been Pn equal to Un outer product of this. Now since it has to take care of the degeneracy also, so therefore the I superscript will also come into play. Now imagine the state of the system is ket psi. Let us construct a new state ket psi n as the projection of psi. Now we are given an arbitrary state ket psi, but we have to construct a new state ket psi n which will take care of the degeneracy, right? Now in this case, the construct a new state psi n as the projection of psi onto the Gn dimensional subspace associated with single lambda n. Now we are going from this ket psi to ket psi n. How we are going from here to here? We are applying a projection operator onto psi. Now this projection operator is basically taking care of the degeneracy. So this factor we have already taken from this point, and we have substituted for Pn here. Now if you just do a little manipulation, this inner product will be equal to a scalar value. This is given by Cn, and we write the new state as this. Now if we try to calculate the norm of this state, we have ket, we need to find out the bra from here, and you can find out the norm. So if you try to find out the norm here, it will be equal to sigma I equal to 1 Gn mod of Cn I square. That means the probability of that particular eigenvalue will be given by the summation of all the squared magnitudes of the coefficients. Which coefficients? For those eigenvalues vectors for which the eigenvalue is same. So that's the probability of this eigenvalue. And if we try to, if we just look into the norm equation again, the probability is given by this inner product of sigma n with itself. Then we can just obtain the equation like this. You just have to do a little bit manipulation. What you have to assume is this is bra psi n. Let us assume identity here and psi n. Since identity has got no effect on either the bra part or the ket part, so we can introduce an identity in between. And we know that this identity, we know that the operator adjoint and the operator itself, when you multiply the two, it is basically identity, right? So we can replace this identity with the multiplication of the adjoint of the projection operator and the projection operator. And since the projection operators are also idempotent, that means the square of the projection operator is equal to the projection operator itself. So therefore we are able to obtain this equation. Why we have put the probability of lambda n equal to this form or this form? Because this is also the expected value of the projection operator. So that is why we have tried to bring this probability equation, the probability of lambda n, into this form. Okay, let me just clear the notes. Okay, so all right. Now let's move further. So this is the probability of lambda n, which is actually the expected value of the projection operator onto the subspace spanned by the eigenstates associated with the eigenvalue. Now let us look into the state collapse and postulate 5. State collapse in quantum mechanics. We know that, so this is the this is the eigenvalue equation. We know that if the measurement of A in the system in state psi, so let us say a system is in state psi and we are trying to measure property A. Now this measurement will give an eigenvalue lambda n. One of the eigenvalues it will give, right? Now once you get the measurement outcome, and that measurement outcome is one of the eigenvalues of this operator, now the state of the system will be eigenvector corresponding to this eigenvalue, and this will be ket un. Now, so therefore, the state ket psi, which is the quantum superposition state, will collapse. This state will collapse and it will go to the eigenstate ket un. So therefore, that's what is I am trying to show here. You are given with ket psi, you try to measure A, you have a set of eigenvalues. Postulate 5 says that you will get one of the eigenvalues, which is lambda n, and you will, the quantum state will be the resultant quantum state will be ket un corresponding to this lambda n. Now you cannot go back from this eigen state or ket un state to ket psi. So this is known as state collapse, and it means that the state psi of the system before measurement collapses to eigenstate ket un. Now, if we are dealing with the degeneracies, then will have to modify the postulate 5. Modified postulate 5 due to degeneracy. Now, if the measurement of A in a system in the state ket psi gives eigenvalue lambda n, then the state of the system immediately after the measurement is normalized projection of psi onto the subspace spanned by the eigenvalue. The essential message of the postulate 5 remains unchanged. The state of the system ket psi changes after measurement and it becomes new state, which is associated with the eigenvalue that we have measured. So if let us say lambda n is, if it is a case of non-degenerate, then the projection vector will be this, and this will be the final state. But if it is a case of degenerate eigenvalues, then we have to certainly, as I just tried to explain, that you have to bring in the Gn subspace also. Then you will have to finally take care of the this collapsed quantum state, and you have to bring in the degenerate subspace also into the final measurement state. Without the degeneracy, it is ket un, but with degeneracy, of course, now you know that you have to take care with the I superscript. Thank you very much.